Hi there. So a student has asked me to go over some of the functions and limits that appear in the improper integral section. So we're going to do a little side lecture just reviewing some of these functions and how to take the limits as x goes to infinity or t goes to infinity or whatever appears in the improper integral definition. Okay, so we start off with the simple functions that are 1 over x to some power. So let's say we had f of x is equal to 1 over x. Okay, now if we just take a look at this graph, we see that for positive x, it looks something like this. Okay, the classic hyperbola kind of shape. Now, if we take the limit as x approaches 0 from the positive side of 1 over x, then the denominator is going to get much smaller. Okay, it's going to go to 0. And so the fraction as a whole is going to go off to infinity. However, if we take the limit as x goes to infinity, then this fraction is going to get smaller and smaller because the denominator is getting bigger. And so the fraction will tend towards 0. So we have the limit as x goes to infinity of 1 over x. This goes to 0. Okay, now this is true for any power of x in this case. So if we have f of x is equal to 1 over x squared, for example, this looks very similar to 1 over x. However, it goes to 0 much quicker. So it's going to look something like this. Okay, but we still have that decay of the function going to 0. And we also have the fact that if x goes to 0, this goes to infinity. So if we take the limit as x approaches 0 plus of 1 over x squared, this also goes to infinity. And if we take the limit as x goes to infinity of 1 over x squared, this will also go to 0. Okay, that's because the denominator is getting larger and larger, and so the fraction as a whole will get smaller and smaller. So in the limit, it goes to 0. Okay, now this works for any power as well. So if we have f of x is equal to 1 over x to the p, for example, where p is greater than 0. Okay, so remember, if you have a negative power, then this gets taken to the numerator again, so we don't want that. So in this case, it's going to be the same thing. It's going to be a decreasing function like this. The limit as x goes to infinity. Oh, let's do 0 first. 0 plus 1 over x to the p. This is going to be equal to, well, not equal to, it's going to go to infinity. And the limit as x approaches infinity, 1 over x to the p, that's going to go to 0. Okay, because the function is going down to 0. Okay, so that's your standard power laws, taking the limits. So next we're going to be looking at exponentials. So you can either have e to the x or e to the minus x. Those are the two that we typically work with. So if we have e to the x, we know that it looks like that. So in this case, if we take the limit as x goes to infinity of e to the x, this is going to go to infinity because we see that as we go to the right, the function just gets bigger and bigger. However, if we go to the left and we take the limit as x approaches minus infinity of e to the x, then this is going to go to 0. Okay, because if we follow this line to the left, it's going to go down to 0. Now, if we look at the flipped version, if we look at e to the minus x, it's going to look like this. Now, in this case, we have the reverse. So the limit as x goes to infinity of e to the minus x, that's going to go to 0 now. Okay, because if we follow this to the right, it's going to go down to 0. If we follow this to the left, then the limit as x approaches, minus infinity of e to the minus x, this is now going to go to infinity. So you see how the limits have swapped because we've got this minus x over here. Okay, so the minus x will swap the limits over there. Okay, so instead of being an increasing function, if we have e to the minus x, it now becomes a decreasing function. Okay, so let's look at the cousin of e to the x, and that is the natural log of x. So what happens when f of x is equal to the natural log of x? Okay, so let's just draw a little sketch so we see what this looks like. We know that it has to go from minus infinity, passes through 1, and then steadily increases like that. Okay, so we know that it comes from minus infinity when x is equal to 0. So the limit as x approaches 0 plus, okay, we can't take negative values, so it has to be from 0 plus, of the natural log of x, this is going to go to minus infinity. Okay, so it diverges when x goes to 0. And when x goes to infinity, natural log of x, this also goes to infinity. So it may look like the graph is leveling off and appearing to be constant. However, the natural log of x is unbounded. So as x goes to infinity, the function also goes to infinity. So the natural log of x is unbounded. Okay, so if you look at the picture, it might seem like it's going to level off and become constant. However, it doesn't do that. It goes all the way up to infinity. Okay. So the next thing that we need to look at is tan and tan inverse, because that appears quite often. So if we have a look at tan, okay, so just look at this one over here. Sorry, like that. Okay, we know that there's this asymptote here at pi over 2. Yeah, we've got this other asymptote here at minus pi over 2. Okay, and then you can repeat this shape as you go along for the period of pi going along. Now, we're only interested in minus pi over 2 to pi over 2 because on that subdomain, this function is invertible. So this is tan of x. If we wanted to invert this, we would get arctan of x, and that looks something like this. Okay, and then we've got these horizontal asymptotes now. So the vertical asymptotes from tan of x become the horizontal asymptotes of arctan of x, or tan inverse. Okay, so the upper asymptote, that's going to be pi over 2. The lower asymptote, that's going to be minus pi over 2. Now, what happens if we take the limit as x goes to plus or minus infinity? Well, for tan inverse, if we take the limit as x goes to infinity of tan inverse of x, this is going to go to pi over 2. Because if we look back at our original tan, then tan of pi over 2 goes to infinity. So if we invert that and look at arctan, then the limit as x goes to infinity of arctan will give you back pi over 2. Okay, there's always this back and forth between the original function and its inverse. Now, if we take the limit going the other way, okay, minus infinity of arctan of x, this is going to give us minus pi over 2. Okay, reason being is that the tan of minus pi over 2 goes to minus infinity. So if we flip that around, and we take the limit as x goes to minus infinity of arctan of x, we're going to get back minus pi over 2. Okay, so just keep in mind that the vertical asymptotes at pi over 2 and minus pi over 2 for tan of x now become the horizontal asymptotes pi over 2 and minus pi over 2 for arctan of x. Okay, so we've just flipped this function over in the process of taking the inverse. Okay, so just to go over one more thing. If you ever have a function like this, f of x is 1 over 1 plus x squared plus x cubed minus x to the 4, if you want to write anything like this and you want to take the limit, remember that we're taking the limit, for example, as x goes to infinity. Okay, if we do this limit, then that will be the limit as x goes to infinity of 1 over 1 plus x squared plus x cubed minus x to the 4. We see that x is going to get larger and larger as x goes towards infinity, which means this term over here, this x to the 4 term, will be the dominant term in the denominator. So for larger and larger x to the 4 is going to grow much larger than the other terms. Okay, that's because x to the 4 is greater than x to the 3, greater than x squared, greater than 1 for large x. Okay, so that's not true for small x, but it is true for large x. So this minus x to the 4 becomes the dominant term. In other words, this function for large enough x looks something like minus 1 over x to the 4. Okay, for large enough x, we can ignore those smaller terms there. And again, we've done this before. If you have 1 over x to some positive power, then this is going to go to 0. Okay, so even though the function may look complicated, remember your limit laws that you learned about last year. You can still take the limit because this is continuous. We can use our limit laws. And also note that if you have dominant terms, you can treat those as your only terms and ignore the less dominant terms. Like in this case, x to the 4 is going to be much larger than the other terms. So we can actually treat this as minus 1 over x to the 4 for large enough x. Okay, and that gives you an idea of what the limit should be. Okay, so I hope this was helpful. If you do have any more questions on functions and how to take their limits, please let me know through email or on the WhatsApp group. I can help you out some more. Okay, so remember that this is important only for the improper integral section, where we have the bounds being, one of the bounds or both of the bounds being infinite. Okay, so then you have to take the limit as x goes to infinity or t goes to infinity, something like that. Okay, so if you do have any questions, please let me know, and then I'll see you in the next lecture. Bye.